Hello and welcome to this video which contains everything that you need to know about Chapter 2 Polynomials for NCERT textbook for CBSE or ICSE boards. This video contains all the exercises, examples, theory, etc. for the NCERT textbook. It has introduction, it has geometrical meaning of the zeros of a polynomial. It has all the exercises like 2.1, exercise 2.2, exercise 2.3 and exercise 2.4. It also talks about a summary at the end and details the relationship between zeros and coefficients of a polynomial. But before you do that, you have to do a small thing. Please subscribe to our channel and like our videos. And also please feel free to share our videos and talk about our channel on the Facebook, WhatsApp and other social media. This is a long video and it contains everything you need to know for the NCERT mathematics textbook for ICSE or CBSE board. In between, there are messages like this one, which request you to subscribe, share or like our channel. During those portions of the video, you can take a break or you can skip those portions of the video. Also remember that you can get the links for the individual portions of this video from a playlist, and this playlist is given in the description of this video.
Welcome to this session on Mathematics, Chapter 2 Polynomials for Class 10 or Grade 10. We are covering Section 2.1 Introduction. Polynomials in one variable x are the algebraic expressions which consist of terms in the form a multiplied by x raised to power n, where n is a non-negative, that is positive or a zero integer, and a is a real number which is also called as the coefficient of the term. Degree of a polynomial in one variable x is the highest exponent or the biggest power of x in that polynomial. Now let's take some examples. 4x plus 12. This is a polynomial. This is a polynomial with variable x, and this is a polynomial with the degree 1 because highest power of x is 1. Another example, 22y square minus 33y minus 444. This is a polynomial. This is a polynomial with variable y, and this is a polynomial with degree 2 because the highest power or the biggest power of variable y in this whole expression is 2. Another example, 25x cube minus x square plus x minus square root of 12. This is a polynomial. This is a polynomial in variable x, and this is a polynomial with degree 3 because the highest power of x, that is variable x, has got the biggest power or the biggest exponent is 3. There are some other expressions. For example, 8 minus square root of 2x. This is not a polynomial because the power of x is not an integer. Another expression, 1 divided by x minus 8. This is not a polynomial because power of x, that is power of the variable, is negative. Let's take one example of a polynomial. Let it be 3x cube plus 4x square plus 5. In this entire polynomial, items like 3x cube or item, let's say 4x square or 5, each one of them is called as a term of the polynomial. So 3x cube is one term, 4x square is another term, and 5 is another term. Also, we see in this polynomial, 3 is the coefficient of x cube because 3 is the number by which x cube gets multiplied. So 3 is the coefficient of x cube. Similarly, 4 is the coefficient of x square, and 5 is the coefficient of x raised to power 0, or 5 is a constant term. Also, a polynomial in one variable could have any number of terms. In the example here, we have shown only 3 terms, 3x cube, 4x square, and 5. But in general, there could be any number of terms in a given polynomial. Now let's see what are linear polynomials. Linear polynomials are the polynomials which have degree of 1. Examples are 3x minus 3, square root of 33 multiplied by x, y plus square root of 112. Quadratic polynomials are also called as square polynomials, and they have a degree of 2. Examples are 2x square plus 2x minus 5 divided by 11, square root of 3 multiplied by y square plus 55, or another example is y square plus square root of 2. Cubic polynomials are the polynomials of degree 3. Some examples are 2x cube plus 2x square minus 5 divided by 11, 3x cube plus 3x square plus 3, y cube plus square root of 2. Now let's have a look at the general form of linear polynomials. The general form is ax plus b, or ax raised to power 1 plus b, where a, b are the real numbers and a is not equal to 0. Because if a were to be 0, then this term, that is ax, will become 0 and we shall be left with only b, and hence the polynomial will no longer be a linear polynomial. The quadratic polynomials have a general form of ax square plus bx plus c, where a, b and c are the real numbers and a is not equal to 0. And again, a is not equal to 0 because if a were to be equal to 0, then term ax square will become 0 and we shall be left with bx plus c, which is not necessarily, or which is not a form of a quadratic polynomial. Similarly, general form of cubic polynomials is ax cube plus bx square plus cx plus d, where a, b, c and d are the real numbers and a is not equal to 0. If we extend it, then we can say general form of a polynomial is px is equal to an multiplied by x raised to power n plus an minus 1 multiplied by x raised to power n minus 1 plus an minus 2 multiplied by x raised to power n minus 2 plus so on up to a0, which is only a0 because it is multiplied by x raised to power 0, which is 1. In this expression, all the an's are the real numbers. So an minus 1 and an minus 2, they are all real numbers. And an's are called as the coefficients of the terms. So let's say an minus 1 multiplied by x raised to power n minus 1. In this term, an minus 1 is the coefficient, and the variable in this case, in this term, has x raised to power n minus 1 as its power is n minus 1. And an, which is the coefficient of the highest term, x raised to power n in this polynomial, cannot be equal to 0, because there will be, if this coefficient were to be 0, then there will be no term in x raised to power n. Now let's see what are zeros of a polynomial. Zeros of a polynomial are also called as roots of the polynomial, and these are the values of the variable x which make the polynomial become equal to 0. So if px denotes a polynomial in variable x, then if for a given x, let's say we are given x is equal to k, and if pk becomes 0, then k is called as a 0 of the polynomial. We can put it in more formal manner and say a real number k is called as a 0 of the polynomial px if pk is equal to 0. Let's take an example. Let's say px is equal to 2x square minus 5x plus 2 is the given polynomial. And now let's start placing different values of x in this. Let's start with x is equal to 0. Then the value of px becomes 2 multiplied by 0 raised to power 2 minus 5 multiplied by 0 plus 2, which is equal to 2. And when x is equal to 1, the value of px becomes 2 multiplied by 1 square minus 5 multiplied by 1 plus 2, which is equal to minus 1. And when x is equal to 2, then the value of px becomes 2 multiplied by 2 square minus 5 multiplied by 2 plus 2, which is equal to 0. That is, we can say that when x is equal to 2, the value of polynomial is 0. That is, 2 is a 0 of the polynomial px. Similarly, when the value of x is equal to half, then the p half, that is value of the variable px, becomes 2 multiplied by half square minus 5 multiplied by half plus 2, which is equal to 0. And we can say that half is a 0 of the polynomial px. So in this example, we can say that 2 and 1 by 2 are the zeros of the given polynomial 2x square minus 5x plus 2. Welcome to this session on Mathematics, Chapter 2 Polynomials for Grade 10 or Class 10. We are covering Section 2.2 Geometrical Meaning of the Zeros of a Polynomial. We know a real number k is a zero of the polynomial px if pk is equal to 0. That is, if the value of x is equal to k, then if we put that into the expression of the polynomial, we will see that the entire polynomial px becomes 0. In simple words, we can say that 0 of a polynomial is that value of x which makes the given polynomial equal to 0. And now let's take some example. Let's take an example where y is equal to 2x plus 1, and 0 of this polynomial will be that value of x which makes this polynomial equal to 0. So let's write it as y is equal to 2x plus 1 is equal to 0, which can be written as 2x plus 1 is equal to 0, and that will give us x is equal to minus 1 by 2. So we can say that x is equal to minus 1 by 2 is a 0 of the given polynomial, and the given polynomial here is 2x plus 1. Let's first see the general format of a linear polynomial, which is px is equal to ax plus b, where a is not equal to 0. To find the 0 of this polynomial, we can say that px is equal to ax plus b will be equal to 0 when ax is equal to minus b, and in other words it can say that when x is equal to minus b by a, the value of the polynomial will be 0, and hence x is equal to minus b by a is a 0 of this polynomial. And let's call this as our statement number 1. Now let's take an example. Let's take example px is a polynomial. Let's also write it as y, which is equal to 2x plus 3. And from this statement number 1, we know that 0 of a linear polynomial is given by minus b by a. So we can find, or we can say that 0 of this given polynomial is minus b by a, which is equal to minus 3 by 2. On the other hand, from our knowledge of geometry, we know that the plot or the graph of y is equal to 2x plus 3 will be a straight line, as is shown in the diagram here, and we know that this straight line will intersect the x-axis at a point minus 3 by 2 comma 0, which is shown here as this is the point, and if you notice, this is the point on the x-axis. So we know that the value of this polynomial y is 0 when x is equal to minus 3 by 2. And let's call this as our statement number 4, and we have this statement number 3 here. And from statements 2 and 3, we can state that the geometrical meaning of the 0 is that 0 of a linear polynomial, in our case it is 2x plus 3, is same as the x coordinate of the point where the graph of y is equal to 2x plus 3 intersects the x-axis. So let's summarize our understanding. We know that the general form of a linear polynomial is ax plus b. We know that 0 of a linear polynomial is given by minus b by a. That is, if the general form is ax plus b, the 0 will be minus b by a. The graph of linear polynomial is a straight line, as is shown in this diagram or example here also. And we know that the straight line intersects the x-axis only at one point. and the coordinate of this one point where the line intersects the x-axis is minus b by a comma 0. So that is the point which is shown here, where the intersection of this line is happening with the x-axis. So we can write the geometrical meaning of 0 as the linear polynomial has exactly one 0, and this 0 is equal to the x coordinate of the point where the graph of y is equal to ax plus b intersects the x-axis. Or in other words, we can say that 0 of a polynomial is equal to x coordinate of the point of intersection, and which is equal to minus b by a. Welcome to this session on Mathematics, Chapter 2 Polynomials for Class 10 or Grade 10. We are covering Section 2.2 Geometrical Meaning of the Zeros of a Polynomial, and in this session we are talking about graphs of polynomials. So we are trying to find out how do graphs of polynomials look like, and let's begin with the constant functions and the linear polynomials, and we will try to see how do their graphs look like. Our first example is px is equal to 4. It is a polynomial which is a constant function. That is, value of this function will remain same for all the values of x. So let's say x becomes 1, it will give us the value of polynomial as 4. When x becomes 4, again the polynomial value will remain 4. That is, the polynomial is a constant function. The other example that we are taking right now is px is equal to 2x plus 2. This is example of a linear function. It's called linear function or a linear polynomial because the maximum power of variable x in this case, it is 1. So it's a linear function. So now we are trying to see how do the graphs of these two types of functions or polynomials look like. So here it is. The plot or the graph of px is equal to 4 is plotted in this diagram, and we see that this is a horizontal straight line which cuts the y-axis on a point 4. So when y is equal to 4, this is the intersection which is happening, and it's a horizontal line. Similarly, the plot of 2x plus 2 is a straight line, but it's not a horizontal line. This line has its slope and it intersects the x-axis at a point. Here in this case it is minus 1. So we can say that the graphs of linear and the constant functions are straight lines. So now let's try to see how do the graphs of quadratic functions or quadratic polynomials which have degree of 2, how do they look like? So we are trying to find out the graphs of, let's take examples of px is equal to x square, px is equal to 2x square, or px is equal to 4x square. So we are now trying to see the graphs of quadratic functions and see how do they look like. So here is our normal x-axis and y-axis. We plot px is equal to x square and we get a parabolic shape. So this parabola is kind of you can say opening upwards, so it is open upwards. Now let's plot px is equal to 2x square, and this is another parabola which is little bit inside the previous parabola. And then let's plot px is equal to 4x square, which is another parabola opening upwards and it is inside. So we see that as the coefficient of x square, we see as we are changing it or as we are increasing it, the graph is stretching vertically. So from x square, when the coefficient is increased to 2x2, from here the coefficient is 1 and here the coefficient is 2. So when we move from 1 to 2, the graph is moving inwards or is stretching along the y-axis. And then when we move the coefficient or when we make the coefficient from 2 to 4, the graph or the parabola is compressed, you can say, or is moving or is stretching more vertically along the y-axis. So but what happens when the coefficient of x square is negative? Because in all these three examples we have considered the coefficient to be positive. So here it is positive 1, here it is positive 2, here it is positive 4. But what happens when the coefficient of x square is negative? So let's see how do the graphs look like when the x square coefficient is negative. So for that case, let's say we are taking examples px is equal to minus x square, px is equal to minus 2x square, and px is equal to minus 4x square. And in these cases, the values of px becomes negative, and all the graphs will become reflected along the x-axis. That is, they will become mirror image of the graph as if the coefficients were positive. So let's first draw, and then we will talk about it a bit more. So this is our x-axis and the y-axis. We have taken them two of such pairs, and let's plot p is equal to x square, and let's also plot p is equal to minus x square. So here you see, as we were talking about, along the x-axis, that is along this x-axis, we see that the two polynomials or the two functions are mirror images of each other. Now let's plot px is equal to 2x square, and let's also plot px is equal to minus 2x square. Let's also plot px is equal to 4x square. This is our third function here, and we also plot px is equal to minus 4x square. So we see that when the coefficient of x square becomes negative, the graph is becoming like a mirror image, or is getting reflected along the x-axis. So if to just remove the lines here, and let's see how does this look like. If you were to use the same pair of x-axis and y-axis, you can see that they look like images of each other. And along the x-axis, if you were to put that like kind of a mirror, you will see as if these things are getting reflected. So graph, when the coefficient of x square is negative, the graph becomes reflected along the x-axis. So now let's take the next case and see, instead of varying the coefficient of x square, why don't we vary the coefficient of x? So let's see what happens when we vary the coefficient of x instead of coefficient of x square. And we will do that by first taking examples. Let's take example functions as x square plus x. Another example we have x square plus 2x. Another we have is x square plus 4x. You will notice that here the coefficient of x is changing. First of all, it is 1, then the coefficient of x is 2, and then the coefficient of x is 4. So this is our axes, x-axis and y-axis. Let's plot the first function, x square plus x, and this is not to scale, but more or less this will look like the shape that is shown here. Now let's plot px is equal to x square plus 2x, and then let's plot the third function, x square plus 4x. So we see that as we are increasing the coefficient of x from x to 2x, or meaning coefficient is changing from 1 to 2 and then from 2 to 4, the parabola or the graph is shifting left. So graph is moving towards left, and it is also moving down a little bit. So we can say that as we increase the positive coefficient of x in a polynomial, the polynomial's graph moves downward and to the left. So let's see, if you see from green then brown to blue, the graph is moving left, and it is also moving down a little bit. So now let's consider what happens when the coefficient of x is becoming negative and we increase it. So here the coefficient, so far we have talked about the coefficient of x being positive, but now we shall talk about the coefficient of x being negative, and we increase it. Again, we will take some examples. First example is px is equal to x square minus x. Then we have x square minus 2x. Then we have x square minus 4x. So here you will see that the negative value, or the absolute value of the negative coefficient, is increasing from minus 1, then it is becoming minus 2, and then it is becoming minus 4. And here is our axes, y-axis and x-axis. And the first, let's plot x square minus x, which is a small parabola here, and then let's plot x square minus 2x, and then we have our third plot, x square minus 4x. So here we see that as the absolute value of the negative coefficient is increasing, the graph is moving rightwards and it is also moving a bit downwards. So you see green is becoming brown, and then the brown is becoming blue here. So we can say that as we increase the negative coefficient of x, and we are increasing it in the absolute value in a polynomial, then the polynomial's graph moves down and to the right. Here if you see, the graph is moved to the right, and it is also moved a little bit down. So now we shall start talking about next case, that is what happens when we vary the constant term in our polynomial. So if you see here, we have x squared and we have x, but we do not have any constant value here. So let's now talk about that scenario. And we shall start that discussion of a quadratic function having x squared, x, and the constant term. So let's take the examples. The first example is x squared plus x plus 0. Our constant here is 0. The other example is x squared plus x plus 1. So the constant term here is 1. And another example is x squared plus x plus 5. And the constant term here is 5. X squared plus x and minus 5. So the constant term here is minus 5. So you see here that we have not changed the values or the terms in x squared and x, but we are varying the constant term in the different polynomials. And now let's see how do their graphs look like. So if we plot them on our usual x-axis and y-axis, these four functions will look like this. So the graph of x squared plus x plus 0 is plotted right here. Then x squared plus x plus 1 is plotted here, and x squared plus x plus 5 is plotted here, and the last function is plotted in here. And you will notice that as we vary the constant term in the polynomial graphs moves upward or downwards. So if you see from here, let's say we had 0 and then we had 1. So from 0 term here to 1, the graph has actually moved upwards. So like this. And also we note that the value of the constant term is the point at which the graph intersects the y-axis. So if you take, for example, let's say this polynomial x squared plus x plus 0, and this is plotted here, and this plot is intersecting the y-axis at 0. And now let's take the plot of x squared plus x plus 1, which is plotted here, and it is intersecting the y-axis at the value 1. So you will notice that the constant term here, it is 1, and the intersection of the graph is happening at the value 1. Here in this example, x squared plus x plus 0, the constant term is 0, so the intersection is also happening at the value 0. And let's say here in this example, px is equal to x squared plus x minus 5. The graph is plotted here, and this graph intersects the y-axis at the value minus 5, which is same as the constant terms value. So we can say that, I will repeat here, that as we vary the constant term in a polynomial, the polynomial's graph moves up or down vertically, and the value of the constant term is the point at which the graph intersects the y-axis. Now also we have seen that how do the graphs of different polynomials look like. We have seen the quadratic polynomials, constant functions, and the linear polynomials or linear functions. Now let's talk briefly about the turning points in the polynomials. And generally speaking, a polynomial of degree n can have up to n minus 1 turning points. So if a polynomial has degree 4, it can have up to 4 minus 1, that is 3 turning points. But what are those turning points? A turning point of a function is the point where the graph of the function changes the direction of the slope. So if the slope were downwards, then turning point is the point where the slope starts becoming upwards, or vice versa. Vice versa means that the slope might be turning upwards, and then when the turning point comes, the slope becomes or turns downwards. And in other words, we can say that the gradient of the function changes from negative to positive or positive to negative. And now let's talk about some shapes or some turning points in different types of functions. So a quadratic function has a degree of 2, and therefore, as we just talked about here, that the maximum number of turning points it can have is 2 minus 1, that is 1. And that indeed is the case, because a quadratic function's graph generally looks like this parabola, and here is the turning point here, where the slope is coming first of all downwards, and then after the turning point it goes upwards. Similarly, the cubic functions, these are the functions which have degree 3, so at the most they can have 3 minus 1, that is up to 2 turning points. Any given graph can have less than 2 also, but the maximum number of turning points in a cubic function's graph will be only 2. And here are the examples. We have this plot, and the turning point number 1 is here, turning point number 2 is here, and then similarly another plot we see here, which is having only one turning point right here. Now, next, let's consider quartic functions which have degree 4, and we know that at the most they can have 3 turning points. And here is the example of our quartic function. It has 1 turning point, 2 turning points, and 3 turning points. So turning point, and this is the maximum number of turning points that we can have in a quartic function. Welcome to this session on Mathematics, Chapter 2 Polynomials for Class 10 or Grade 10. We are talking about Section 2.2 Geometrical Meaning of the Zeros of a Polynomial, and in this session we shall talk about the quadratic polynomials. For a quadratic polynomial which has a general form of ax squared plus bx plus c, where a is not equal to 0, we can have the graph of the corresponding equation, which is y is equal to ax squared plus bx plus c. We notice that this graph is of the parabolic shape. Parabolic shape is something like this, or we have a shape like this. And we notice that when a, which is the coefficient of x square, when this a is positive, the parabola opens upward like this. And if the value of a, which is the coefficient of x square, is negative, the parabola opens downwards like this. So we have it here like a less than 0, the parabola will open downwards, and when a is greater than 0, the parabola will open upwards. So what's the geometrical meaning of zeros of a quadratic polynomial? The zeros of a quadratic polynomial ax squared plus bx plus c, where a is not equal to 0, are the x coordinates of the points where the graph representing y is equal to ax squared plus bx plus c intersects with the x-axis. And we can show this by taking an example. Let's say the example is x squared minus 3x minus 4. Let's say this be the given polynomial. And from the graph of this polynomial, x squared minus 3x minus 4, which is plotted here, we notice that this graph intersects the x-axis at 2 points, which are minus 1, 0, and 4 and 0. So these points are here, which is minus 1 and 0, and this one is 4 and 0. So the x coordinate of these 2 points are minus 1 and 0. So if you see, this 4 is here and this minus 1 is here. So we notice that the graph intersects the x-axis at 2 points, and the x values or x coordinates of these 2 points are minus 1 and 4. Also, value of polynomial y is equal to x squared minus 3x minus 4 will be 0 when x is equal to 4 or x is equal to minus 1. So we notice that x is equal to 4 and minus 1 are the zeros of the given polynomial. And from the statement 1 here, we notice that these values are nothing but the x coordinate values for the points where the graph of this polynomial intersects. So we have shown from these statements 1 and 2 that the zeros of a quadratic polynomial are the x coordinates of the points where the graph representing y is equal to ax squared plus bx plus c intersects the x-axis. So when the graph of the polynomial, a quadratic polynomial is a parabola, then there are three scenarios which arise. The first scenario is that the graph intersects the x-axis at 2 points. The second is that the graph intersects the x-axis at 1 point. And then the third scenario is that the graph does not intersect the x-axis at all. So in scenario 1, the polynomial in this case will have two distinct zeros. So we have the scenario 1, which is that the parabola or the graph of the polynomial is intersecting the x-axis at two distinct points, and in that 2 points, or in that scenario, the polynomial will have two distinct zeros. The scenario 2 is that when the graph intersects the x-axis at 1 point only. So in that scenario, or in that case, the polynomial will have only 1 0. And this scenario is shown here like this. The third scenario is that the graph does not intersect the x-axis at all. So in this scenario, the graph of the polynomial is either completely above the x-axis, or it is below the x-axis and does not intersect the x-axis at all. In this case, the polynomial has no zero at all. So we can summarize these scenarios as scenario 1, when the graph intersects the x-axis at two distinct points, the polynomial has two distinct zeros. When the graph intersects the x-axis at 1 point, the polynomial has two equal zeros, which is basically saying as they have only 1 0. The scenario 3 is that the graph does not intersect the x-axis. In that case, polynomial has no zero at all. And also we see that the quadratic polynomial, which has degree 2, can have a maximum of 2 zeros only. Welcome to this session on Mathematics, Chapter 2 Polynomials for Class 10 or Grade 10. We are covering Section 2.2 Geometrical Meaning of the Zeros of a Polynomial, and in this section we shall be covering cubic polynomials. Geometrical meaning of the zeros of a polynomial which is of cubic type, that is cubic polynomial. For that we say that the zeros of a cubic polynomial ax cubed plus bx squared plus cx plus d, where a is not equal to 0, are same as the x coordinates of the points where the graph representing y is equal to ax cubed plus bx squared plus cx plus d intersects the x-axis. This geometrical meaning we can show using an example, and let's take the example as y is equal to x cubed minus 4x. So zeros of this polynomial are -2, 0 and 2. We conclude this using this table, which is nothing but a plot of values of x and then the value of y, or you can say values of x cubed minus 4x here. So for different values of x, we get different values of this polynomial, and we notice that this polynomial x cubed minus 4x is equal to 0 when the value of x is -2. Again, the value of this entire polynomial x cubed minus 4x is 0 when the value of x is 0. And again, this value of the entire polynomial is 0 when the value of x is 2. So from here we conclude that if you see this point and this point and this point, from these 3 points which are highlighted, we can say that the zeros of the given polynomial are -2, 0 and 2. Also, if we plot the graph of this function, so here we have plotted the graph of this function, and actually you can plot this graph using this table itself. So when you plot this graph of x cubed minus 4x, we notice that this graph intersects the x-axis at 3 points, and these 3 points are minus 2, 0, 0, 0 and 2, 0. So when these are the three coordinates of the 3 points where the intersection of x-axis and the graph is happening, let's see what is the value of the x coordinate points. The values of x coordinate points in these 3 points is minus 2, 0 and 2. And these three numbers or these three values are same as the zeros of the given polynomial, which we already found here. So by these two statements or the bullet points that we have here, we can say that the geometrical meaning of the cubic polynomial of ax cubed plus bx squared plus cx plus d, where a is not equal to 0, we can say that the zeros are same as the x coordinates of the points where the graph representing y is equal to ax cubed plus bx squared plus cx plus d intersects the x-axis. Also, for any cubic polynomial, we say that it has at the most 3 zeros. And if we generalize it for any polynomial, we can say that for a polynomial px which has a degree of n, the graph of y is equal to px intersects the x-axis at the most n points. So n is the maximum number of points where the graph y is equal to px can intersect the x-axis, and hence we say that the polynomial px of the degree n can have at the most or the maximum n zeros. Let's now look at the example number 1, and this says look at the graphs given below. Each is the graph of y is equal to px, where px is a polynomial, and for each of the graphs find the number of zeros of px. So let's start solving this, and we see that the first graph given to us is this, and we say that the number of zeros of this polynomial px is 1. And why this is 1? This is because the graph of y is equal to px intersects the x-axis only at one point, and that one point is this point, because this is the only point at which the intersection of x-axis and the graph is happening. And since it is only one point, we say that the zeros of the polynomial px is 1. The second part or the second graph given to us is this, and we say that the number of zeros of the polynomial px in this case is 2, because the graph of y is equal to px intersects the x-axis at 2 points, and these 2 points are this point and this point. The third graph given to us in this example is this graph, and we say that the number of zeros of the polynomial px in this case is 3, because the graph of y is equal to px intersects the x-axis at 3 points. And what are those 3 points? This is point number 1, this is point number 2, and this is point number 3. The fourth part of this example is giving us this graph, and we say that the number of zeros of the polynomial px in this case is 1, because the graph of y is equal to px intersects the x-axis at 1 point, and this point of intersection is this here. And let's take a look at the fifth part, and the graph given to us is this graph. In this case, the number of zeros of the polynomial px is 1, because the graph y is equal to px intersects the x-axis at 1 point, and that 1 point is this point here. In the part 6th or the last part of this example, we are given this graph, and the number of zeros of the polynomial px in this case is 4, because the graph y is equal to px intersects the x-axis at 4 points, and these 4 points are point 1, 2, 3 and 4. Welcome to this session on Mathematics, Chapter 2, Polynomials for Class 10 or Grade 10. We are doing exercise 2.1 in this session. Exercise 2.1, question number 1. The question number 1 states the graphs of y is equal to px are given below for some polynomials px. Find the number of zeros of px in each case. The first graph given to us is this, and we say that the number of zeros of the polynomial px in this case is 0 because the graph of y is equal to px intersects the x-axis at no point. That is, there is no point of intersection between the x-axis and the graph of this polynomial. And you can see that the x-axis is this, the graph of the polynomial is this. They are both parallel and there is no point of intersection. Hence, the zeros of the polynomials are 0, meaning there are no zeros of this polynomial. The second graph given to us is this, and the number of zeros of the polynomial px is 1 because y is equal to px intersects the x-axis at one point, and this one point is this point here. The third graph given to us is this graph, and the number of zeros of the polynomial px is 3 because the graph of y is equal to px intersects at the x-axis at 3 points, and these 3 points are point number 1, point number 2, and the third point here. Let's go to the fourth part, and the fourth graph given to us is this graph, and the number of zeros of the polynomial px in this case is 2 because the graph of y is equal to px intersects the x-axis at 2 points, and these 2 points are point number 1 and point number 2. And let's go to the part number 5 of the question, and the graph given to us is this, and the number of zeros of the polynomial px in this case is 4 because the graph of y is equal to px intersects the x-axis at 4 points, and these 4 points are this point, this point, this point, and the fourth point is this one. Let's now go to the sixth part of the question, and the graph given to us is this graph, and the number of zeros of the polynomial px in this case is 3 because the graph of y is equal to px intersects the x-axis at 3 points, and these 3 points are this point, point number 2, and the point number 3. Welcome to this session on Mathematics, Chapter 2 on Polynomials for Class 10, Grade 10. We are covering relationship between zeros and the coefficients of a polynomial. In this session, we shall be talking about the relationship between zeros and the coefficients of a polynomial of type linear, type quadratic, cubic, quartic, and also we shall give the formulae of relationship between zeros and coefficient for a polynomial of general form of degree n. Let's start with the linear polynomials, and we know that linear polynomials will have at the most one zero, and let's represent that zero by letter alpha. Also, the linear form of the polynomial is ax plus b, which once solved will give us the value of the zero of the polynomial, that is alpha, as equal to minus b by a. Now this equation is our relationship between the zeros of the polynomial and its coefficients. Let's now talk about the quadratic polynomials. We know that a quadratic polynomial will have at the most two zeros, and let's represent those two zeros by the letters alpha and beta. If alpha and beta are the zeros of the polynomial, then x minus alpha and x minus beta will be the factors of the given polynomial. Therefore, we shall be able to write the polynomial ax square plus bx plus c equal to k times x minus alpha times x minus beta. Here you notice that x minus alpha is a factor of the polynomial, x minus beta is a factor of the polynomial, and k is a constant term. And of course, a is not equal to 0 because if it were to be 0, then the polynomial will no longer be a quadratic polynomial. Once we simplify the right hand side, we get ax square plus bx plus c is equal to k times x square minus k alpha plus beta x plus k alpha beta. Now let's compare different terms in this equation, or the coefficients of x square, coefficient of x, and the constant term on both sides of this equation. Once we compare the coefficient of let's say we compare the coefficient of x square, we notice that the coefficient of x square on the right hand side is k and on the left hand side it is a. Therefore we get the equality a is equal to k, and let's call this as our statement number 1. Now let's compare the coefficient of x on both the sides. The coefficient of x on the right hand side is minus k times alpha plus beta, and on the left hand side this coefficient of x is b. So if we compare these two coefficients, we get alpha plus beta is equal to minus b by k. That is equal to alpha plus beta is equal to minus b by a. And of course we are using here the fact that a is equal to k, which we deducted or deduced from the statement number 1. Similarly, if we compare the constant term on both the sides, we get k alpha beta is equal to c, that is c is equal to k times alpha beta, and this gives us alpha beta is equal to c divided by a. So now if we summarize our understanding or what we have deduced so far, we can say that alpha plus beta is equal to minus b by a, which is equal to minus coefficient of x divided by coefficient of x square, and the product of the zeros, that is alpha times beta, is equal to c by a, which is equal to constant term divided by the coefficient of x square. And let's take an example of the quadratic polynomial. Let it be 2x square minus 4x plus 1. In this case, a is equal to 2, b is equal to minus 4, c is equal to 1. Therefore, our sum alpha plus beta, sum of zeros, will be minus b by a, which will be equal to minus of minus 4 divided by 2, which is equal to 2. Similarly, the products of the zeros, alpha times beta, will be c by a, and in our case c is equal to 1 and a is equal to 2. So c by a, that is product of the zeros, will be 1 by 2, which will be equal to half. Now let's take to the next level and let's talk about the relationship between zeros and the coefficients of the cubic polynomials. We know that a cubic polynomial will have at the most 3 zeros, and let us show them by 3 letters: alpha, beta, and gamma. And if alpha, beta, and gamma are the zeros of the polynomial, then x minus alpha, x minus beta, and x minus gamma will be the factors of the given polynomial. Therefore, we shall be able to write the given polynomial ax cubed plus bx square plus cx plus d as equal to k times x minus alpha, x minus beta, x minus gamma, where you can notice that x minus gamma is a factor, x minus beta is a factor, x minus alpha is a factor, and k is a constant term. So we will simplify the right hand side, and we get to write this right hand side as kx cubed minus k times alpha plus beta plus gamma x square plus k times alpha beta plus alpha gamma plus beta gamma times x minus k alpha beta gamma. So now if we were to compare both the sides of this equation, we can compare the coefficients of x cube, x square, x, and the constant term, or we can compare different, or we can say that we are comparing different terms on both the sides. We notice that on comparison of coefficients of x cube, we get a is equal to k, and let's call this as our statement number 1. Similarly, if we were to compare the coefficients of x square on both the sides, we notice that on the right hand side the coefficient of x square is minus k times alpha plus beta plus gamma, and on the left hand side the coefficient of x square is b. So if we put them both equal to each other, we get alpha plus beta plus gamma is equal to minus b by a. Similarly, comparing the coefficients of x, we get alpha beta plus beta gamma plus alpha gamma is equal to c by a. And if we compare the constant term, we get alpha beta gamma is equal to minus d by a. And of course, in this comparison, we are using the term or the statement number 1, which is a is equal to k. So if we summarize our relationships between zeros and the coefficients of a cubic polynomial, we say that sum of zeros S1 is alpha plus beta plus gamma is equal to minus b by a. Second sum of zeros, S2 is equal to alpha beta plus beta gamma plus alpha gamma is equal to c by a. And finally we have alpha times beta times gamma is equal to minus d by a. And let's see an example, which is x cubed minus 6x squared plus 11x plus 6. And this is of the form ax cubed plus bx squared plus cx plus d. Here a is equal to 1, c is equal to 11, b is equal to minus 6, and d is equal to 6, which gives us the first sum of zeros as s1 is equal to alpha plus beta plus gamma is equal to minus b by a, which is equal to minus 6 divided by 1, but it whole half this has to be taken as a minus, so we get it as 6. Similarly, second sum of zeros will be s2, which will be equal to alpha beta plus beta gamma plus alpha gamma, which will be equal to c by a, and in our case it will be equal to 11 by 1, that is 11. Similarly, product of zeros alpha beta gamma will be minus d by a, which is equal to minus of 6 divided by 1 in our case, and hence it gives us minus 6. Let's now move on to quadratic polynomials. These are the polynomials which have degree 4, and they are sometimes called as biquadratic polynomials. Their general form is ax4 plus bx cubed plus cx squared plus dx plus e, where a is not equal to 0. And now let's represent their 4 zeros as alpha, beta, gamma, and delta. Their first sum of the zeros, that is S1, will be equal to alpha plus beta plus gamma plus delta, will be equal to minus b by a, that is minus of the coefficient of x cube divided by the coefficient of x raised to power 4. Similarly, the second sum of the zeros will be S2 will be equal to alpha beta plus beta gamma plus gamma delta plus alpha gamma plus alpha delta plus beta delta. This will be equal to c by a. The third sum of the zeros, S3, will be equal to alpha beta gamma delta, alpha beta delta, beta gamma delta, and this sum will be equal to minus d by a. And the fourth sum of the zeros will be S4 will be equal to alpha beta gamma delta, and this will be equal to e divided by a. Let's now move on to general form of polynomials. We know that the general form of polynomials is represented as a0 x raised to power n plus a1 x raised to power n minus 1 plus a2 x raised to power n minus 2 and so on up to an multiplied by x raised to power 0. In this form, an is not equal to 0 and n is a non-negative integer. We also know that a polynomial of degree n will have at the most n zeros. So let's represent those n zeros by letters alpha 1, alpha 2, alpha 3, alpha 4 and up to alpha n. Also, if alpha 1, alpha 2 and up to alpha n are the zeros of the polynomial, then x minus alpha 1, x minus alpha 2, x minus alpha 3 and so on up to x minus alpha n will be the factors of the given polynomial. Therefore, we can write the given polynomial to be equal to the multiplication of these factors and this whole multiplied by a constant term a0. So we have now an equation, that is the given polynomial is equal to the multiplication of its factors. So we can say that the given equation is a0 times x raised to power n plus a1 multiplied by x raised to power n minus 1 plus a2 multiplied by x raised to power n minus 2 and so on is equal to the a0 times x minus alpha 1 times x minus alpha 2 times x minus alpha 3 and so on up to x minus alpha n. So this is our equation where we have different coefficients of different powers of x. So now let's start comparing the coefficients of different powers of x and let's see what do we get. Let's now start comparing the coefficients of different powers of x on two sides of the equation 1. Let our first coefficient for comparison be the coefficient of x raised to power n minus 1. This will give us the first sum s1, which is alpha 1 plus alpha 2 plus alpha 3 and so on up to alpha n. And in simple form, it is written as sigma alpha I. And this sum will be equal to minus a1 divided by a0, which is equal to minus coefficient of x raised to power n minus 1 divided by the coefficient of x raised to power n. Next, let's compare the coefficients of x raised to power n minus 2 on both sides of the equation 1, and this will give us the second sum S2, which is equal to alpha 1 times alpha 2 plus alpha 1 times alpha 3 plus alpha 1 times alpha 4, and so on. And in simple form it is written as sigma I not equal to j alpha I alpha j, and this sum will be equal to minus 1 square times a2 whole divided by a0. Next, let's compare the coefficients of x raised to power n minus 3 on both sides of the equation 1, and this will give us the third sum S3, which is alpha 1 alpha 2 alpha 3 plus alpha 2 alpha 3 alpha 4 plus alpha 3 alpha 4 alpha 5, and so on. And the simple form of this sum is sigma I not equal to j not equal to k alpha I alpha j alpha k, and this sum will be equal to minus 1 raised to power 3 a3 divided by a0. And similarly we can find fourth sum, fifth sum, and so on. But what will be the general nth sum here? Let's see, or let's find that out by comparing the coefficients of x raised to power n on both sides of the equation 1. The nth sum Sn will be equal to alpha 1 alpha 2 alpha 3 and multiplied up to alpha n, and this sum will be equal to minus 1 raised to power n an divided by a0, which is equal to minus 1 raised to power n times the constant term divided by the coefficient of x raised to power n. Hi, welcome to this session on Mathematics, Chapter 2 on Polynomials. For class 10 or grade 10, we are doing exercise 2.2, question number 1. Question number 1 states, find the zeros of the following quadratic polynomials and verify the relationship between zeros and the coefficients. Answer 1, part 1, x square minus 2x minus 8. This can be written as x square minus 4x plus 2x minus 8, and once simplified it gives us this polynomial is equal to x plus 2 multiplied by x minus 4, and this implies that either x plus 2 is equal to 0 or x minus 4 is equal to 0, and both these imply that either x is equal to minus 2 or x is equal to 4. Hence we can say that the zeros of the given polynomial are minus 2 and 4. So now let's verify that the relationship between the coefficient is as what we know. So first let's see the sum of the zeros. We have already found the zeros as minus 2 and 4. So the sum will be equal to 2, and which indeed is equal to minus b by a, because the b in the given polynomial is minus 2 and minus b by a is equal to minus of minus 2 by 1, which is equal to 2. Hence we have verified this relationship. Similarly, we see that the product of the zeros which we have found just now is equal to minus 2 into 4, and this gives us minus 8, and this minus 8 is indeed equal to c divided by a, because c divided by a is equal to minus 8 by 1, that is minus 8. Hence we have verified the relationship between coefficients and the zeros. Next, answer 1 part 2, 4s square minus 4s plus 1. This can be written as 4s square minus 2s plus 1, which gives us, or which is equal to 2s minus 1 multiplied by 2s minus 1, which implies s is equal to 1 by 2. And again, because there are this term 2s minus 1 is twice, so we can say that we have two zeros for this polynomial, and both of those zeros are equal. So we have first zero as 1 by 2, the second zero is also 1 by 2. So we have found the two zeros of the given polynomial. Now let's start the verification process. The sum of the zeros is 1 by 2 plus 1 by 2 is equal to 1. This is what we have gotten because we found the two zeros to be 1 by 2 and 1 by 2. Now this sum, or this 1, is indeed equal to minus b by a, because minus b by a is equal to minus of minus 4 divided by 4, which is equal to 1. So we have verified this relationship. Similarly, the product of the zeros will be 1 by 2 multiplied by 1 by 2, which is equal to 1 by 4, and which will be equal to c by a, and which is equal to 1 divided by 4, which is equal to the constant term divided by the coefficient of x square. Hence, we have verified the relationship between 0 and the coefficients. Answer 1, part 3, 6x square minus 7x minus 3. This can be written as 6x square minus 9x plus 2x minus 3, which will be equal to 3x plus 1 times 2x minus 3. Hence, we can say that either the x is equal to minus 1 by 3 or x is equal to 3 by 2. That is, the zeros of the given polynomial are minus 1 by 3 and 3 by 2. Now let's verify. So first see what's the sum of the zeros that we have found. This 0 will be equal to minus 1 by 3 plus 3 by 2, which is equal to 7 by 6. And this sum is indeed equal to minus b by a, because b is minus 7. So minus b by a will be 7 by 6, and that 7 by 6 is equal to the 7 by 6 that we found by summing up the zeros that we found. Similarly, product of the zeros will be minus 1 by 3 multiplied by 3 by 2, which will be equal to minus 1 by 2. And this minus 1 by 2 is equal to c by a, because in the given polynomial c is minus 3. So we have c by a is equal to minus 3 by 6, which is equal to minus 1 by 2, and which is equal to the same value that we found by multiplying the zeros that we had found here. So hence we can say that we have verified the relationship between coefficients and the zeros as well. Now let's go to the answer 1, part 4. We are given 4u square plus 8u, which is equal to 4u times u plus 2, which implies that either u is equal to minus 2 or u is equal to 0. That is, we have found the zeros of the given polynomial as 0 and minus 2. So now let's start the verification process. So the sum of the zeros which we just found out will be 0 plus minus 2, which will be equal to minus 2. And this sum is indeed equal to minus b by a. That is, in our case, in the polynomial we are given the value of b is 8 and minus b will be minus 8, a will be 4. So this minus b by a will be equal to minus 2, and that indeed is equal to the sum that we found by adding up the zeros that we calculated. So this relationship has been verified. Similarly, the product of the zeros will be 0 multiplied by minus 2 is equal to 0, which is equal to c by a, which is equal to 0 by 4, because c in our case is 0, hence it is equal to 0, and we have verified the relationship between coefficient and the zeros. Let's now talk about answer 1, part 5. We are given t square minus 15. To find zeros of this polynomial, let's make this polynomial equal to 0. That is, t square minus 15 is equal to 0, which implies t is equal to plus or minus of square root of 15. So we get the zeros of this given polynomial as minus 15 square root or plus of square root of 15. In fact, there is another way to find the zeros of this polynomial, and let's see that another way. We note that the given polynomial is t square minus 15, which is of the form a square minus b square if b is square root of 15. That is, t square minus 15 is equal to t square minus square root of 15's square. And we know that a square minus b square is equal to a minus b multiplied by a plus b. So this entire given polynomial will be equal to t minus square root of 15 times t plus square root of 15. So comparing or trying to get the zeros, we get that t minus square root of 15 will be equal to 0, or t plus square root of 15 will be equal to 0. Then by doing this comparison, we get that the zero of the given polynomial are minus square root of 15 plus square root of 15. So we have found the zeros of the polynomial as minus 15 or plus 15. And now let's do the verification. Sum of the zeros will be minus square root of 15 plus square root of 15, which will be equal to 0. And this indeed is equal to minus b by a, because b in our case is 0, and this b by a will become 0 by 1, which is 0. The product of the zeros will be minus square root of 15 multiplied by square root of 15, which will be equal to minus 15, and which actually is equal to c divided by a, because c by a is equal to minus 15 by 1, which is equal to minus 15. Hence, we have verified the relationship. Next, let's consider the answer number 1, part 6. We are given 3x square minus x minus 4, and this can be simplified to be written as x plus 1 times 3x minus 4, which implies either x plus 1 is equal to 0 or 3x minus 4 is equal to 0. And by doing this, we get the value of x as x is equal to minus 1 or x is equal to 4 divided by 3. That is, now we have found the zeros of the given polynomial as minus 1 and 4 divided by 3. So let's now do the verification. Some of the zeros that we just found will be equal to minus 1 plus 4 by 3, which is equal to 1 divided by 3, which is equal to minus b by a. Similarly, product of the zeros will be minus 1 multiplied by 4 by 3, which is equal to minus 4 by 3, which indeed is equal to c by a. Welcome to this session on Mathematics, Chapter 2 on Polynomials for Grade 10 or Class 10. We are doing exercise 2.2, question number 2. Question number 2 states, find a quadratic polynomial, each with the given numbers as the sum and product of its zeros respectively. Before we start solving this question, let's recall the following. That a quadratic polynomial has at the most two zeros, and let us represent those two zeros by the letters alpha and beta. If alpha and beta are the zeros of the polynomial, then x minus alpha and x minus beta will be the factors of the given polynomial. And we shall be able to write the given polynomial, let's say a prime x square plus b prime x plus c prime is equal to k times x minus alpha times x minus beta, which once simplified will be equal to a prime x square plus b prime x plus c prime is equal to kx square minus k times alpha plus beta x plus k times alpha beta. And if we divide both sides by k, we shall get ax square plus bx plus c is equal to x square minus alpha plus beta x plus alpha beta. So here we notice that on the right hand side, the coefficient of x is equal to minus of alpha plus beta, which is equal to the minus of sum of the zeros of the polynomial. And similarly, the constant term is alpha beta, which is also equal to the c, which is here. And the constant term here we can say that is equal to multiplication of the zeros of the polynomial. Let's now start solving the question number 2. Let's start with question number 2, part 1. We know that for a quadratic polynomial with two zeros alpha and beta, we can write ax square plus bx plus c is equal to x square minus alpha plus beta x plus alpha beta. And now we notice that what we are given here is that sum of the zeros is equal to 1 by 4 and the product of the zeros is minus 1. So let's enter these two values into our equation or the statement number 1, and based on that we get the quadratic polynomial as x square minus 1 by 4x plus minus 1, which when solved will give us 4x square minus x minus 4. So we get the required polynomial which we were to find out is equal to 4x square minus x minus 4. The answer number 2, part 2, we know that a quadratic polynomial is of the form 4x square plus bx plus c, and this is equal to x square minus alpha plus beta x plus alpha beta, and let's call this as our equation number 1. And in this question we are given sum of the zeros as square root of 2 and product of the zeros is given to us as 1 divided by 3, and let's put these two values into our equation number 1, and based on that we get the equation of the quadratic polynomial, or we get the quadratic polynomial as x square minus square root of 2x plus 1 by 3, which when one simplified will give us 3x square minus 3 square root of 2 times x plus 1. Answer number 2, part 3. we know the quadratic polynomial with two zeros alpha and beta can be written as ax square plus bx plus c is equal to x square minus alpha plus beta x plus alpha beta. And now in this question we are given sum of the zeros as 0 and the product of the zeros is given to us as square root of 5. We will put these two values in the equation number 1 and we will obtain the quadratic polynomial as x square minus 0x plus square root of 5, which once simplified will give us the polynomial as x square plus square root of 5. Answer to part 4. We know that the quadratic polynomial can be written as ax square plus bx plus c, which can be further written as x square minus alpha plus beta x plus alpha beta. In our question, we are given sum of the zeros as 1 and the product of the zeros is also to be 1. This is given to us. Let's enter these two values in this equation and based on that we get the polynomial as x square minus 1x plus 1, which gives us the polynomial as x square minus x plus 1, and this is our answer. Now do the answer number 2 part 5. We know that the quadratic polynomial can be written as ax square plus bx plus c, which is equal to x square minus alpha plus beta x plus alpha beta. We are given here the sum of the zeros as minus 1 divided by 4 and the product of the zeros is given to us as 1 divided by 4. We will enter or put these two values in the equation number 1 and based on that we will get the quadratic polynomial as x square minus of minus 1 by 4 x plus 1 by 4, which when we simplify it will be equal to 4x square plus x minus x plus 1. Now let's do the answer number 2 part 6. We know that for the quadratic polynomial we can write it to be equal to x square minus alpha plus beta x plus alpha beta. Here in this question we are given sum of the zeros as 4 and the product of the zeros is given as 1. We will put both these values which are given to us in this equation number 1 and we shall obtain the quadratic polynomial as x square minus 4x plus 1, which can be written as here x square minus 4x plus 1, and this is our required polynomial or required answer. Welcome to this session on mathematics, chapter 2 polynomials for class 10 grade 10. We are doing division algorithm for polynomials. Before we proceed ahead, let's recall what is a divisor, what is a dividend, what is a quotient, or what is a remainder. For doing this, let's recall a picture which is of the long division algorithm from the simple arithmetic. And this picture shows that a divisor is generally kept on the left hand side, a quotient is on the top, dividend is inside the division symbol, and the remainder is at the bottom. It also clearly shows that a dividend is equal to divisor multiplied by quotient plus the remainder. And in our example here, we can see 13 is the dividend, which is equal to 3 times 4 plus 1, where 1 is the remainder and 4 is the quotient and 3 is the divisor. Let's now talk about division algorithm for polynomials, which states that if there are given any two polynomials p1x and p2x, where p2x is a non-zero polynomial, that is p2x is not equal to 0, and the degree of p1x is greater than or equal to the degree of p2x, then there exist unique polynomials qx and rx such that p1x is equal to p2x times qx plus rx, where rx is equal to 0 or the degree of rx is less than the degree of polynomial p2x. And if we show this picture, we can see that the divisor is represented by p2x, quotient is qx, dividend is p1x, and the remainder is polynomial rx. Also, sometimes we denote these polynomials p1x and p2x as polynomials px and gx respectively. And in that case, the division algorithm, which is represented by this equation, it will become the equation px is equal to gx times qx plus rx. That is, the division algorithm will be written as px is equal to gx times qx plus rx. Also, sometimes we write this as px divided by gx is equal to qx plus rx by gx. Before we end this session, let's also talk about the remainder theorem for polynomials. This theorem states that if a polynomial p1x is divided by x minus k, then the remainder is the value of the function p1x at x is equal to k. That is, the value of the remainder is given by p1k. To show this theorem is true, let's substitute the value of p2x as x minus k. That is, we are replacing the polynomial p2x by x minus k in the division algorithm. And if we do that, we get the polynomial p1x is equal to x minus k times qx plus rx. And also we know that the division algorithm states that the degree of Rx is less than the degree of the divisor. So here our divisor is x minus k, which has the degree of 1. Therefore, the degree of Rx has to be less than 1. So the degree of Rx has to be equal to 0. And for a polynomial which has degree 0 is called as a constant function or a constant polynomial. So we can replace Rx and show it as just R here. So what we get is that p1x is equal to x minus k times qx plus r. And now, in order to get the value of this polynomial p1x at the x is equal to k, we substitute x is equal to k in this equation, and we get p1k is equal to k minus k times qk plus r, which is equal to 0 times qk, that is polynomial q with value x is equal to k plus r, and which is equal to r. That is, p1k is the remainder when p1x is divided by x minus k. Welcome to this session on Mathematics, Chapter 2 Polynomials for Class 10 or Grade 10, and we are doing division algorithm for polynomials, and we are doing the steps now. We have already seen in a previous session what does the division algorithm for polynomial states, and that statement is repeated here. More details are given in the previous session, but in this session we shall cover the steps for this algorithm. So we shall be talking about the algorithm, that is the steps to divide one polynomial by another polynomial. Remember that we stop the division process when the remainder becomes 0 or the degree of the remainder becomes less than the degree of the divisor. And to understand the steps, we shall take the example to divide minus 13x square plus 4x cube plus 2x minus 8 by x square plus 3x minus 2. And before I proceed ahead, let me show you the complete picture of the entire division. And this is how the division looks like, and we write our final answer as 4x minus 25 plus 85x minus 58 divided by x square plus 3x minus 2. Let's now get to the detailed step for the division algorithm. Step 1 states that write the given polynomials, dividend as well as the divisor, in the standard form. That is, ensure that the polynomials are written in the descending order of their degrees, and this is what actually the standard form is. And if any term is missing in the polynomial, use a 0 to fill in the missing term. because this filling up by 0 helps in spacing when we divide. So in our example, we will have to rearrange the dividend, and the new arrangement would look like 4x cubed minus 13x squared plus 2x minus 8. And this rearranged term is written inside the division symbol. Step 2a. In order to get the first term of the quotient polynomial, divide the largest degree term of the dividend, and dividend is written inside the division symbol, and its largest degree term is this, because the largest degree is x cube or the degree 3, and the whole term is 4x cube. And the step says that we divide it by the largest degree term of the divisor, and the largest degree term of divisor is this. So we shall be, in our example, dividing 4x cubed by x squared, and in doing so we get 4x. The next step is 2b, which says that multiply what you got in the previous step, that is multiply this 4x in our example by the complete divisor polynomial, which is outside the division symbol. So we will multiply, in our case, we will multiply the divisor, this whole polynomial is divisor, and we shall multiply it by 4x, which is what we got from the previous step. The next step is step 2c, and in this case, or in this step, we carry out the subtraction and bring down the next term. So we will subtract this 4x cubed plus 12x squared minus 8x, and after subtraction we will be left with minus 25x squared plus 10x, and then we shall bring down this next term down here as it is. So minus 8 is dropped down and it comes down here. The next step is step number 3, which says repeat the steps 2a, 2b and 2c until there are no more terms to bring down. That is, in order to get the second term of the quotient polynomial, divide the largest degree term of the new dividend, that is leftover polynomial inside the division symbol, by the largest degree term of the divisor, which is outside the division symbol, and in our case this is the divisor. So the example what we are working with, will do step 2a in again, and in that case we will divide minus 25x squared by x squared, and in doing so we will be left with minus 25, and then we will multiply this minus 25 by the complete divisor, which is x squared plus 3x minus 2, and then we shall carry out the subtraction. So this step is shown here, and we carry out the subtraction of minus 25x squared minus 75x plus 50, and then we are left with 85x minus 58. The step 4 is carry out the division process, that is step 2 a, b and c, until the remainder term, that is leftover polynomial inside the division symbol, is either 0 or has a degree less than the degree of the divisor. So in our case we see that after subtraction we are left with 85x minus 58, and there is no term to bring down, and this is not equal to 0, but its degree is 1, which is less than the degree of our divisor, and the divisor has a degree of 2. So our remainder term is 85x minus 58. And then step 5 is to write the final answer. The term remaining after the last subtraction step is called the remainder, and the remainder is written as a fraction in the final answer. So we shall write remainder as a fraction, which is 85x minus 58 divided by the divisor, which is x squared plus 3x minus 2, and our quotient is 4x minus 25. So if you see carefully, 4x minus 25 is coming here as quotient, and we have divisor going below the remainder, and remainder whatever we were left with is 85x minus 58 here. Before we end this session, let's do the verification of division algorithm. We have just seen when we divide minus 13x squared plus 4x cubed plus 2x minus 8 by x squared plus 3x minus 2, we get an answer 4x minus 25 plus 85x minus 58 divided by x squared plus 3x minus 2. Now we shall carry out a few extra steps and do the verification of the division algorithm. We know that by this answer we got the remainder as 85x minus 58, and we got the quotient as 4x minus 25, and the divisor in our case is x squared plus 3x minus 2. So when we multiply these three, multiply the divisor and the quotient and then add the remainder, we will get x squared plus 3x minus 2 multiplied by 4x minus 25 plus 85x minus 58. And once we simplify it, we get this to be equal to 4x cubed minus 13x squared plus 2x minus 8. That is, when we did the divisor multiplied by quotient and then we added remainder, we got in our example 4x cubed minus 13x squared plus 2x minus 8, which indeed is equal to the dividend, because we were given the dividend to be equal to minus 13x squared plus 4x cubed plus 2x minus 8. So we did see here that when the divisor is multiplied by quotient and then the remainder is added, we get the dividend, and hence we have verified the division algorithm as well. Hi, welcome to this session on Mathematics, Chapter 2 Polynomials. For class 10 or grade 10, we are doing division algorithm for polynomials, and in this session we are covering exercise 2.3, question number 1. Question number 1 states, divide the polynomial px by the polynomial gx and find the quotient and remainder in each of the following cases. Answer 1, part 1. We are given dividend is equal to px is equal to x cubed minus 3x squared plus 5x minus 3, and divisor is equal to gx is equal to x squared minus 2. Entire division is carried out in this figure here. All the steps are shown, and I'll just state the first step. Our first step is that we take the highest degree term of the dividend, which is in our case here x cubed, and then we divide it by the highest degree term of the divisor, which is x squared in our case here. Based on this division, we get the term x, which is the first term of the quotient, and then we multiply this term of the quotient to the entire divisor polynomial, and in our case we get this equal to x cubed minus 2x, because we have multiplied x to the x squared minus 2. Then we carry out the subtraction, and then we get minus 3x squared plus 7x, and we drop down the next term, which is minus 3 in our case here, and then we add it or append it to the leftover polynomial. Then we try to find out the next term of the quotient, and in this case we first look at the highest degree term in the leftover polynomial here. In our case now it is minus 3x squared. We then divide it by the highest degree term of the divisor, which is x squared here. So when we divide the minus 3x squared by the x squared, we get minus 3, which is the next degree or the next term in our quotient, and then this minus 3 is multiplied to all or entire divisor, which is x squared minus 2, and we get minus 3x squared plus 6. We subtract this out and carry out this subtraction. We are left with 7x minus 9. There is no more term to bring down. Degree of 7x minus 9, that is our remainder, is less than the degree of the divisor, so we can stop our division process here, and we can say that our answer is remainder is equal to 7x minus 9, and our quotient is x minus 3 here. So our entire answer is quotient is equal to x minus 3 and remainder is equal to 7x minus 9. Answer to question 1 part 2, we are given dividend as px is equal to x raised to power 4 minus 3x squared plus 4x plus 5, and the divisor in our case is gx, x squared plus 1 minus x. The entire steps for the division are shown here, and therefore by this steps we see the quotient is equal to x squared plus x minus 3 and the remainder is 8, and that is our answer. Answer to question 1 part 3. The dividend in our case is px, x raised to power 4 minus 5x plus c. Divisor is gx is equal to 2 minus x square, and here the dividend is shown inside the division symbol. When we carry out the entire division, we are left with minus 5x plus 10, which is our remainder here, and the quotient is minus x square minus 2, which is written over here, and therefore our complete answer is quotient is equal to minus x square minus 2, and the remainder is minus 5x plus 10. Welcome to this session on Mathematics Chapter 2 Polynomials for Class 10 or Grade 10. We are covering in this session exercise 2.3 question number 2. Question number 2 states, check whether the first polynomial is a factor of the second polynomial by dividing the second polynomial by the first polynomial in these given cases. Answer to part 1. We are given dividend is equal to 2t4 plus 3t cube minus 2t square minus 9t minus 12, and the divisor is given as t square minus 3. We carry out the entire division, and these steps show the complete division here. The divisor is on the outside of the division symbol. Dividend is inside the division symbol here. You would notice that in the divisor we have added a term 0t because it helps in the spacing of the terms that we are using in different steps. So we carry out the entire steps, entire division is carried out here, and we get the quotient is equal to 2t square plus 3t plus 4, and the remainder is 0. Since the remainder in this case is 0, we can say that the polynomial t square minus 3 is a factor of the polynomial 2t raised to power 4 plus 3t cube minus 2t square minus 9t minus 12. Answer to part 2. We are given dividend as 3x raised to power 4 plus 5x cube minus 7x square plus 2x plus 2, and the divisor is given to be x square plus 3x plus 1. We write the divisor here outside the division symbol. Dividend is written inside the division symbol, and we carry out the entire division. We get, by carrying out this division, the quotient equal to 3x square minus 4x plus 2. This is the quotient here, and the remainder in our case here will be 0. So we notice that the remainder in this case is 0. Hence, the polynomial x square plus 3x plus 1 is a factor of the polynomial 3x raised to power 4 plus 5x cube minus 7x square plus 2x plus 2. Answer to part 3. The dividend given to us is x raised to power 5 minus 4x cube plus x square plus 3x plus 1. The divisor given to us is x square minus 3x plus 1. We place the divisor outside the division symbol, and the dividend goes inside the division symbol. We carry out the steps for the division, and we get the quotient is equal to x square minus 1, and the remainder that we get here is 2. In this case, the remainder is not equal to 0. Hence, the polynomial x square minus 3x plus 1 is not a factor of polynomial x raised to power 5 minus 4x cube plus x square plus 3x plus 1. Hi, welcome to this session on Mathematics, Chapter 2 on Polynomials for Class 10 or Grade 10. We are doing division algorithm for polynomials, and we are covering in this session exercise 2.3, question number 3. Question number 3 states that obtain all other zeros of polynomial 3x raised to power 4 plus 6x cube minus 2x square minus 10x minus 5 if two of its zeros are square root of 5 by 3 and minus square root of 5 by 3. We note that degree of this polynomial is 4. Therefore, the maximum number of zeros that this polynomial can have is 4. Also note that if a minus b and a plus b are factors of a polynomial, then the multiplication of these two factors, that is multiplication of a minus b and a plus b, will also be a factor of the polynomial. And we know that multiplication of a minus b and a plus b is equal to a square minus b square. Therefore, we can say that a square minus b square is also a factor of the polynomial. So now let's start by writing our given polynomial as px, so that px is equal to 3x raised to power 4 plus 6x cube minus 2x square minus 10x minus 5. And if the square root of 5 by 3 and minus square root of 5 by 3 are zeros of the polynomial px, then x minus square root of 5 by 3, and here we are getting square root of 5 by 3 from here because that is one of the zeros. We can say that x minus square root of 5 by 3 and x plus square root of 5 by 3 are factors of polynomial px. This means that the multiplication of these two factors, that is x minus square root of 5 by 3 multiplied by x plus square root of 5 by 3, which is equal to x square minus 5 by 3, is also a factor of px. So now we know that x square minus 5 by 3 is a factor of px. So let's divide the given polynomial px by this factor x square minus 5 by 3, and then we should get the remainder to be equal to 0, because x square minus 5 by 3 is a, let's say, proper factor of polynomial px. Okay, so now that we are dividing polynomial px by x square minus 5 by 3, and the steps to carry out that division are shown here. We have the factor here x square minus 5 by 3 written here. We have added a term 0x so that spacing is very easy during the division process. And we get the quotient as 3x square plus 6x plus 3. And we know that dividend is equal to divisor into quotient plus remainder. And in our case, we have gotten the remainder as 0. And we have gotten the quotient as 3x square plus 6x plus 3. And this is here. So we write this quotient here. And the divisor in our case is x square minus 5 by 3. So here we have now gotten px is equal to x square minus 5 by 3 into 3x square plus 6x plus 3. So we can further simplify by taking 3 common from the second factor. We get px is equal to 3 multiplied by x square minus 5 by 3 into x square plus 2x plus 1. Now if we start simplifying the last factor, that is x square plus 2x plus 1, we can further write px is equal to 3 into x square minus 5 by 3 into x square plus x plus 1. And you would notice that here these two first factors are as it is from the previous step, and here the last factor we have simplified further, and we have written x square plus 2x plus 1 as x square plus x plus 1. So this will help us write px to be equal to 3 multiplied by x square minus 5 by 3 into x plus 1 whole square. Now if we have to make this px is equal to 0 to get the additional zeros that we have to find out, we can try to equate different parts of the right hand side equal to 0. So first is that when 3 is equal to 0. When 3 is equal to 0, then the entire polynomial px will become 0, and hence we can say that the 0 of the polynomial is 3. But we know that 3 is not equal to 0, so we do not consider this factor. So let's move on to the second part. The second factor on the right hand side is x square minus 5 by 3, and if we make this equal to 0, the entire polynomial px will become 0. So let's see what is the value of x when this factor x square minus 5 by 3 becomes 0. We see that when x is equal to square root of 5 by 3, or x is equal to minus square root of 5 by 3, this entire polynomial px becomes 0. So we can say that x is equal to square root of 5 by 3 and x is equal to minus square root of 5 by 3 are zeros of the polynomial. This is true, but these are the zeros which we have already been given in the question. So that is not our objective. Our objective is to find the additional zeros. So let's move on to the third part or the third factor of the right hand side, and we see that this entire polynomial px will be equal to 0 when x plus 1 whole square will be equal to 0, and this will be equal to 0 when x is equal to minus 1, and x again we are writing it twice because there is a whole square. So when x is equal to minus 1, then this whole factor x plus 1 whole square will become 0, and hence at that time px will be 0. So we can say that x is equal to minus 1 and x is equal to minus 1 are the two additional zeros that we were set out to find of the given polynomial. Hence we can write all the four zeros of the given polynomial. The first zero is square root of 5 by 3, the second zero is minus square root of 5 by 3, and the next zero is minus 1, and the next zero is minus 1. So we can say that we have found the zeros, the additional zeros of the polynomial as minus 1 and minus 1. Hi, welcome to this session on Mathematics Chapter 2 Polynomials for Grade 10 or Class 10. We are doing division algorithm for polynomials, and in this session we are covering exercise 2.3 question number 4. Question number 4 states on dividing the polynomial x cube minus 3x square plus x plus 2 by a polynomial gx, the quotient and remainder were x minus 2, minus 2x plus 1 respectively. Find the gx. We know that the dividend is equal to divisor times quotient plus remainder, and in this question we are given dividend to be equal to x cube minus 3x square plus x plus 2. The divisor is gx, which is to be found out. Quotient is x minus 2, and we are also given remainder as minus 2x plus 4. Now if we input the values of these polynomials into our statement number 1 here, then we get that the polynomial x cube minus 3x square plus x plus 2 is equal to gx times x minus 2 plus minus 2x plus 4. And once we simplify it, we get gx to be equal to x cube minus 3x square plus x plus 2 minus of minus 2x plus 4 divided by x minus 2. And on further simplification, it will give that gx is equal to x cube minus 3x square plus 3x minus 2 whole divided by x minus 2. So now we know that the gx value can be obtained by dividing the polynomial here x cube minus 3x square plus 3x minus 2 by x minus 2. So let's carry out the complete division, and this division is carried out here, and the steps are elaborated in this diagram. Here x minus 2 is our divisor, which is the denominator in this expression here. Our dividend is x cube minus 3x square plus 3x minus 2, which is the numerator from this expression here. Once we solve this, we get a remainder of 0, and our quotient is x square minus x plus 1, and that is the value of gx here. So we have now found out the value of gx to be equal to x square minus x plus 1, and this is our answer. Hi, and welcome to this session on Mathematics, Chapter 2 Polynomials for Class 10, Grade 10. We are doing division algorithm for polynomials, exercise 2.3, question number 5. Question number 5 states, give examples of polynomials px, gx, qx and rx which satisfy the division algorithm, and for 1, degree of px is equal to degree of qx, part 2, degree of qx is equal to degree of rx, part 3, degree of rx is 0. We have already covered in detail the division algorithm and we are just stating it here once again. And we are also repeating the conditions which relate to the division algorithm as a dividend is equal to divisor times quotient plus remainder, that is px is equal to gx times qx plus rx, and if we divide both sides of this equation by gx, we get another form or another expression which says px by gx is equal to qx plus rx plus gx. Another condition in the division algorithm is that gx is not equal to 0. Next is that either rx is equal to 0 or degree of rx is less than the degree of gx. And lastly, we are stating that degree of px is greater than or equal to the degree of gx. So now let's start working on the question number 5. Question number 5, part number 1, degree of px is equal to degree of qx, and let our example px be 20x square minus 20x plus 140, and let the gx be 20. If px and gx are these, then let's carry out p divided by g, and in that case qx will be 20x square minus 20x plus 140 divided by 20, and which will give us the qx as x square minus x plus 7. And therefore we have now found the quotient, that is qx, to be equal to x square minus x plus 7, and our remainder is 0. Now let's see another example for the question number 5.1. Let the px be 20x square minus 20x plus 143, and let our gx be 20. When we carry out the division of px by gx, we get the expression x square minus x plus 7 plus 3 divided by 20. And if we compare this expression by the form that we had gotten from division algorithm, that is px by gx is equal to qx plus rx divided by gx, then we can find, or we can say that the qx is equal to x square minus x plus 7 and rx is 3. And this is there because if we compare this equation x square minus x plus 7 plus 3 by 20, which is of the form x square minus x plus 7 plus 3 divided by gx. So now we are comparing this expression here with this, and we can see that the gx is gx, which is same, qx will be here, which is same as x square minus x plus 7, and 3 will be the rx, that is the remainder. And therefore for this part 1 of question 5, we have found the quotient, we have found the remainder, we already gave example of p, and we gave the g. So now we have solved this part. Let's now go to answer number 5, part 2, degree of qx is equal to degree of rx, and let our examples of px and gx be px is equal to 2x raised to power 6 plus 2x cubed plus 41, and let gx be x raised to power 6 plus x raised to power 3 plus 20. And now when we do division of px by gx, we get 2x raised to power 6 plus 2x cubed plus 41 divided by x raised to power 6 plus x cubed plus 20. This on further simplification, because here we have split 41 into 40 plus 1, and then we further simplified it and we got this px by gx to be equal to 2 plus 1 divided by gx. So now if we compare this with the expression px by gx is equal to qx plus rx by gx, we see the quotient is 2 and r is 1 in our case. Let's also give another example for this question number 5 part 2. Let our example polynomials be px is equal to x raised to power 6 plus x and gx be x raised to power 5. In that case, px by gx will be equal to x plus 1 divided by gx. So if we compare it with our expression here, we will see that 1 is the rx, that is remainder is 1, and x will be our qx, and hence we have found the value of q, we have found the value of r, we have already given example of g, and we have given example of p. Therefore we have found all the four values p, g, q and r, and hence we have solved the example of the question number 5-2. Let's go to answer of question number 5, part 3, degree of qx is equal to degree of rx. Let our examples of px and gx be px is equal to 2x raised to power 6 plus 2x cube plus 41, and let the gx be x raised to power 6 plus x cube plus 20. In this case, px by gx is equal to 2x raised to power 6 plus 2x cube plus 41 divided by x raised to power 6 plus x cube plus 20, and if it is simplified we get 2 plus 1 divided by gx, and therefore in this case the qx will be 2 and rx will be 1, and hence we have found the values, or we have given the examples of px, we have given gx, and we have given the value of qx and rx. Let's also see another example for question number 5, part 3. Let our px polynomial be x cubed plus 5, let the gx be x squared. When we do p divided by gx, we get x cubed plus 5 divided by x squared, which implies qx is equal to x and rx is equal to 5, and hence we have found, or we have given the examples, or we have given the answer of question number 5, part 3 as px is equal to x cubed plus 5, gx is equal to x squared, qx is equal to x, and rx is equal to 5. Hi, welcome to this session on Mathematics, Chapter 2 on Polynomials for Class 10, Grade 10. We are doing division algorithm for polynomials, exercise 2.4, question number 1. Question number 1 states, verify that the numbers given alongside of the cubic polynomials below are their zeros. Also verify the relationship between the zeros and the coefficients in each case. Let's solve the question number 1, part 1. We are given the polynomial, and let's denote it by px, that px is equal to 2x cubed plus x squared minus 5x plus 2, and we are also given the number 1 by 2. So let's verify that if 1 by 2 is a zero of this polynomial or not. So p half will be equal to 2 times 1 by 2 raised to power 3, that is this value here, plus half square minus 5 multiplied by half plus 2. Once simplified, this makes px is equal to 0, and since this is equal to 0, the 1 by 2 is a 0 of this given polynomial. So second step is that we will verify that if 1 is 0 of this polynomial, so we find the value of p1, that is when x is equal to 1, and we get that p1 is equal to 0. Hence 1 is a 0 of this given polynomial. Now let's verify if minus 2 is a 0 of this polynomial. When we keep x is equal to minus 2, we get the value of the polynomial is equal to 0. Hence we can say that minus 2 is a 0 of the given polynomial. Therefore by now we have verified that 1 by 2, 1 and minus 2 are zeros of the given polynomial. For the next step, let's denote these three zeros by letters alpha, beta and gamma respectively. Also, we notice that the given polynomial is of the cubic form ax cubed plus bx squared plus cx plus d, where a is equal to 2, b is equal to 1, c is equal to minus 5 and d is equal to 2. So now let's go to the next step of verifying the relationships. But what is the relationship? What is the relationship between zeros of the cubic polynomial and its coefficients? So this equation alpha plus beta plus gamma is equal to minus b by a is the relationship, and now we shall verify it by using the values of the zeros that we found out. That is, we found out or we verified that alpha, beta and gamma are equal to 1 by 2, 1 and minus 2. So now we shall place these values of alpha, beta and gamma into the left hand side of this relationship that we are trying to verify, and then whatever value we get, we will compare it to the right hand side where we will keep the values of a, b and c, which we have just written over here. So let's try to verify the relationship number 1. We see that alpha plus beta plus gamma is equal to 1 by 2 plus 1 plus minus 2, which is equal to minus 1 by 2, which indeed is equal to minus b by a. Therefore, we can say that we have verified the first relationship. The second relationship is alpha beta plus beta gamma plus alpha gamma is equal to c by a. So now let's use the values of alpha, beta and gamma that we verified just now into the left hand side, and we get by this the value of alpha beta plus beta gamma plus alpha gamma is equal to minus 5 by 2, and which we see is indeed equal to c by a when we use the values of c and a from here. So we can say that this relationship has been verified as well. The third relationship is alpha multiplied by beta multiplied by gamma is equal to minus d by a. Now let's use the values that we just verified for the alpha, beta and gamma, and we notice that alpha, beta and gamma is equal to minus 1, which indeed is equal to minus d by a. Hence we can say that we have verified the relationship number 3 also. So in summary, we can say that the relationship between zeros and the coefficients of the given polynomial has been verified. Now let's do the question number 1, part number 2. We are given this polynomial and we have to first verify if that these three numbers are its zeros or not, and then we shall verify the relationship between the zeros and the coefficients of this polynomial. So we denote the given polynomial by px equal to x cube minus 4x square plus 5x minus 2. And let's first verify if 2 is a 0 of this polynomial. We see that value p2 is equal to 0. Therefore, 2 is a 0 of this polynomial. Next, let's try to see if 1 is a 0 of this polynomial, because 1 is another number given to us. So we put this x is equal to 1 and we see p1 is equal to 0. Hence 1 is a 0 of this given polynomial also. So by now we have verified that the numbers 2, 1 and 1 are the zeros of the given polynomial, and now let's denote them by alpha, beta and gamma respectively. Also, we notice that the given polynomial is of the form ax cube plus bx square plus cx plus d, and we can say that in this given polynomial a is equal to 1, b is equal to minus 4, c is equal to 5 and d is equal to minus 2. Therefore, alpha plus beta plus gamma, from the given zeros we know that this is equal to 2 plus 1 which is equal to 4, and this indeed is equal to minus b by a, because b is equal to minus 4 and a is equal to 1. Similarly, alpha beta plus beta gamma plus alpha gamma is equal to 5, which is actually equal to c by a. Similarly, alpha multiplied by beta multiplied by gamma is equal to 2, which is equal to minus d by a when we use the values that we have found here. So we can say that we have verified the relationship between the zeros and the coefficients of the given polynomial. Welcome to this session on Mathematics, Chapter 2 Polynomials for Class 10 or Grade 10. We are doing division algorithm for polynomials, exercise 2.4, question number 2 and 3. Question number 2 states find a cubic polynomial with the sum of the products of its zeros taken 2 at a time and the product of its zeros as 2, minus 7, minus 14 respectively. Answer 2. Let the cubic polynomial be ax cube plus bx square plus cx plus d, and we are given here that alpha plus beta plus gamma, where alpha beta and gamma are the zeros of this polynomial, and we are given here that alpha plus beta plus gamma is equal to minus b by a, which is equal to 2, and which we can write also as 2 divided by 1. We are also given alpha beta plus beta gamma plus alpha gamma, which is actually equal to c by a, is equal to minus 7, and we can write this as minus 7 by 1. Similarly, we are given alpha into beta into gamma, which is equal to minus d by a, which is equal to minus 14 here, and which this minus 14 is the value we are given here, if you notice, and minus 14 can be written as minus 14 by 1. So now if we compare all these three equations, we get the value of a is equal to 1, because if you see this minus b by a, if b is equal to 2, then a can be written as 1. Similarly, in this equation we see that c is the numerator equal to minus 7, a is the denominator 1 here. So we can say that value of a is 1. Similarly, we can find value of b from the first equation here. We have written that minus b by a is equal to 2 by 1, and minus b is the numerator on the right hand side, so it is equal to minus 2. C will be equal to minus 7, because if we see the second equation, numerator is c, which is equal to minus 7, and denominator here is a, and on the right hand side is equal to a 1. So c is equal to minus 7. So now we have found values of a, b, c, and d, and using these values of a, b, and c, and d, which we put in this form, and we get the value of the polynomial as x cubed minus 2x squared minus 7x plus 14, and hence our answer polynomial is this. Question number 3. If the zeros of the polynomial x cubed minus 3x squared plus x plus 1 are a minus b, a plus b, find a and b. Answer. For a cubic polynomial, we know that sum of zeros alpha plus beta plus gamma is equal to minus the coefficient of x squared divided by coefficient of x cubed. And in our case, we are given the values of alpha, beta, and gamma. So we get alpha plus beta plus gamma is equal to a minus b plus a plus a plus b, which becomes minus 3 minus of minus 3 divided by 1, because we are using the coefficients of x square and x cube from the given polynomial. So this equation will imply that 3a is equal to 3, and which once simplified gives us that a is equal to 1, and let's call this as our statement number 1. Let's also note that the product of the zeros for a cubic polynomial, that is alpha into beta into gamma, is equal to minus of the constant term divided by the coefficient of x cube. Therefore, in our case, it will imply that a minus b multiplied by a plus b is equal to minus 1 divided by 1, which implies that a square minus b square into a is equal to minus 1. But now we already have found that a is equal to 1. So we have, from our statement number 1, we know that a is equal to 1. So let's put that into this equation here, and we will get that value of b is equal to plus or minus square root of 2. Hence, we have found the values of a and b as a is equal to 1, b is equal to square root of 2, or square root minus square root of 2. Hi, welcome to this session on Mathematics Chapter 2 Polynomials for Class 10 Grade 10. We are doing division algorithm for polynomials, exercise 2.4, question numbers 4 and 5. Question number 4. If two zeros of the polynomial x raised to power 4 minus 6x cubed minus 26x squared plus 138x minus 35 are 2 plus minus square root of 3, find other zeros. Answer. We know that if k is a zero of a polynomial, then x minus k is a factor of that polynomial. Therefore, in our case, x minus 2 minus square root of 3 and x minus 2 plus square root of 3 are factors of the given polynomial. Also, the product of the two factors is also a factor of the polynomial. Therefore, in our case, the x square minus 4x plus 1, which is a product of the two factors x minus 2 minus square root of 3 and x minus 2 plus square root of 3, is also a factor of the given polynomial, this one. So now we can find the remaining factors, that is we will be able to find the remaining zeros by dividing the given polynomial by x square minus 4x plus 1. So we keep the x square minus 4x plus 1 in the divisor place here, and the given polynomial is kept in the dividend position inside the division symbol, and all the steps to carry out the division are shown here, and we can find that the remainder is 0 and the quotient is x square minus 2x minus 35. Based on the division that we just carried out above, we can write the given polynomial, and you notice that this is the given polynomial, and we can write this polynomial to be equal to x square minus 4x plus 1 multiplied by x square minus 2x minus 35. And when this is simplified, we get x square minus 4x plus 1 multiplied by x minus 7 into x plus 5. And you would notice that the first part of the equation, and this is the first part of the equation, gives us the zeros as 2 plus minus square root of 3. But in order to get the other zeros of the polynomial, let's equate the remaining part of the above equation, and this is the second part or the remaining part of this equation. And now let's equate this to be equal to 0. So we shall have to equate this part, x minus 7 equal to 0 and x plus 5 is equal to 0. And when we do this, we get x is equal to 7 or x is equal to minus 5. Hence we can say that the other two zeros of the given polynomial are 7 and minus 5. Now let's do question number 5, which states if the polynomial x raised to power 4 minus 6x cubed plus 16x square minus 25x plus 10 is divided by another polynomial x square minus 2x plus k, the remainder comes out to be x plus a. Find k and a. In our case, we are given dividend to be equal to this polynomial, divisor to be equal to this polynomial, and the remainder is equal to x plus a. We know that dividend is equal to divisor times quotient plus remainder. Therefore, in our case, we get this equation, and when we rearrange the expression, we get quotient is equal to x raised to power 4 minus 6x cubed plus 16x square minus 26x plus 10 minus a whole divided by x square minus 2x plus k. So this equation, that is this one, implies that the polynomial x raised to power 4 minus 6x cubed plus 16x square minus 26x plus 10 minus a, when it is divided by x square minus 2x plus k, the remainder should be equal to 0. So let's carry out this division. And here we show the division. X square minus 2x plus k is divisor and the dividend is this entire polynomial. We carry out the division and we see that the remainder term is this. That is minus 10 plus 2k times x plus 10 minus a minus 8k plus k square. Therefore, in our case, the remainder will be 0 if both the terms of this expression are 0. So now let's try to equate them to 0. The first term we have is minus 10 plus 2k times x is equal to 0. So this implies k is equal to 5. And the second term is that 10 minus a minus 8k plus k square is equal to 0. And when we simplify this expression, we get a is equal to minus 5. Hence we have found out the answer because we set out to find the values of a and k, which we have found to be a is equal to minus 5 and k is equal to 5.